Welcome to the second part of the module, Energy, Enzymes, and Thermodynamics. Today we're going to start looking at a little bit of thermodynamics. So this is kind of a hybrid between physics and chemistry with some biology tossed in. So let's start with the first law of thermodynamics, and that is a law you're probably familiar with, and that states that neither energy nor matter can be created or destroyed. And so what is going to happen when we look at biological processes is we're going to look at the conversion of matter and energy from one form into another form, and we're going to do this with two sets of biological processes. We'll start out with cellular respiration, and then we'll move on to photosynthesis. And if you get cellular respiration, photosynthesis is much harder, so don't kind of barrel on through cellular respiration thinking that you worry about it when we get a photosynthesis. If you get cellular respiration, photosynthesis is going to be much easier. So that's the first law of thermodynamics. Let's kind of expand on it and put it into the context of biology before we get into too much complicated thermodynamics. So if we think about cellular respiration, all we're going to do here is transform matter that goes into that biological process into the forms of matter that come out of that biological process. So here is the generic equation for describing cellular respiration from a chemical perspective. The reactants that go into cellular respiration are going to be glucose and oxygen, and we're talking about aerobic respirations. There are lots of types of bacteria that can do anaerobic respirations, but we're talking about aerobic respirations. And so we'll look at the glucose that goes in, the oxygen that goes in, and then all that cellular respiration does is it converts the glucose and the oxygen to water and carbon dioxide. And so through a series of many complicated chemical reactions, we're going to take the matter in glucose and oxygen and transform it into the matter in water and carbon dioxide. And so when we say that you can't destroy or create matter, basically this equation has to be balanced. And it's not balanced as I've written it here. There need to be some numbers in here, because just these molecules imply there's one of everything. These numbers here, or the lack of numbers implies there's one of everything. So the matter that goes in the form of glucose and oxygen must be balanced by the matter that comes out in the form of water and carbon dioxide, because thermodynamics prohibits us from creating or destroying matter. And likewise, the energy that is contained in the molecules glucose and oxygen must come out, but it's going to come out in different forms, and we'll look at the forms that it comes out in. And the one that you'll be most interested in is the chemical potential energy form of ATP, but that is only one form that comes out. We have to consider how else the energy comes out as we convert glucose and oxygen to water and carbon dioxide, and that'll be as heat. So we can think about this a little bit graphically as well. So we've got the equation back here, glucose and oxygen converted to water and carbon dioxide by the processes of cellular respiration. So if you look at that graph over there, you're going to see a lot of graphs like this, including on your quizzes and your exam at the end of the semester. Let's think about it like this. The bars represent energy. Okay, the amount of energy that you find in glucose and oxygen, I've just indicated as being 100 here. Don't worry about the units. You could say that's 100%. That works perfectly well if you're comfortable with that. But don't worry about the scale on the y-axis right now. So after the reactions of cellular respiration, when we have carbon dioxide and water coming out of cellular respiration, there's still some energy in those molecules, because they're molecules composed of atoms which occupy space, which means they have some chemical potential energy due to the bonds that link the atoms together. But there's not as much energy in carbon dioxide and water as when in the start of the process in the form of glucose and oxygen. So where does that energy go? Because I just told you that you can't destroy the energy that we start with. So if we start with all the energy over here and we end up with this much energy, this looks like I've evoked some kind of Harry Potter exception to the first law of thermodynamics, because this much energy between the top of this line and the top of the graph is gone. It's got to be accounted for somehow. So some of it will be lost as heat. Just like physical processes, like the processes used in your engine to break gasoline down into carbon dioxide and water, biological processes are not 100% efficient. So we're going to always lose some heat to the universe, and that heat, as far as we're concerned right now, is not biologically useful. There are some cases, for example, brown fat, the mitochondria in brown fat, they actually are going to break fats down to release heat, which is useful for certain processes. If you're hibernating as an animal, for example, that's useful heat to get you through cold winters. But we're not worried about that heat. We're worried about the energy that can be used to do work in your cells. So we call that, or chemists and physicists, I guess, and biologists adopt the convention, we call that energy that can be used to do work free energy. It's free to do work. It can be harnessed and used, and it's given the letter G, a big G, uppercase G. So we're going to talk a lot about free energy. That is the energy that we can take from the glucose and the oxygen, and we can convert to another form, another chemical form, chemical potential energy in the form of ATP. But there's also a whole bunch of other energy that we can't use, and we're not going to worry about that right now. We're going to worry about this energy that can be used to do work, and it's just called free energy. So don't let it freak you out or make you nervous. This is just what we call the energy that's going to be used by the cell to do some work, and it's going to be captured largely in the molecule ATP. So that's the first law of thermodynamics as it applies to cellular respiration. And when we do photosynthesis, we'll look at the same law of thermodynamics, but we'll look at it in the context of photosynthesis. So the second law of thermodynamics says that energy and matter transformations increase entropy. So energy and matter transformations, it doesn't matter what the transformation is, cellular respiration, that's what we're talking about here. They increase entropy. Now, entropy is a complicated concept, it's a complicated topic. It's difficult to explain and difficult to grasp. So, is what you probably heard people say is that entropy is the same as disorder. And I even have chemistry textbooks which say that, and that's wrong. Entropy is not about disorder. We could certainly talk about entropy being synonymous with randomness. If something has high entropy, then there's more randomness, but we can't say that something's disordered. Disorder is an anthropomorphic concept. It's something that humans come up with to describe the world when it doesn't fit into nice compartments that we like. So when we think about entropy, we can think about randomness. That's totally fine. Let's look at the diagram here that we've got. So the diagram over there, let's take a look at that. So there's a ball of matter made up of many, many small pieces, and those pieces are organized into a ball, and so they're not randomly distributed. Each of those pieces of the ball there, which is about to shatter, is occupying a specific space, and so it's limited. It's restricted in the space it can occupy by being non-randomly ordered into this structure. Now, if we take that ball and we kind of explode it, and we end up with all these little tiny pieces that you can see in the diagram over there, the kind of exploded ball, each of those pieces now has the possibility of occupying many, many, many different spots or points in space. And so it's easy to say that's disordered, but that's wrong. This is all about an increase in the distribution of points in space that molecules or atoms can occupy. And so these ones are going to be ordered more randomly. There's no way to predict where they're going to be. But if the ball was actually atoms in a molecule, we would know what's bonded to what because of the nature of the molecule. Now, if we broke that apart into constituent atoms and we let them just move away from each other freely, they can now occupy lots of different points in space, and so there's a much greater distribution of points in space that each atom or molecule could occupy. So if we think about the ball on the left as being glucose and oxygen, in the glucose, the carbons and the hydrogens and the oxygens are all bonded together in a particular way, which gives it a non-random structure. Now, if we break that apart and we make some carbon dioxides and we make some waters and that kind of stuff, those molecules can now diffuse freely. The atoms aren't locked in space in as in a discrete way as they are when they're in glucose. And so they now have the opportunity to exist in many different distributions, and so their entropy has said to be increased. So that's what we say mean when we say that entropy has increased. This is complicated. There aren't many good online explanations of this, so for now that's where we're going to leave it. Free energy is described by the letter G, entropy is described by the letter S. So if we say that entropy is increased, we could say that S has increased. So don't be too upset or worried about these abbreviated names. They are just names. G, free energy, S, entropy. And we're going to look at the relationship between free energy and entropy as we do these chemical transformations during cellular respiration, and later we'll look at photosynthesis, like I say. So let's go back to our equation describing cellular respiration. So when we look at glucose and oxygen being transformed into water and carbon dioxide, like the equation says, is what's going to happen is entropy is going to go up. So let's look at that in a graphical way. So this graph here is showing us what happens to entropy. Now again, don't worry about the y-axis. We're not worried about the scale. This thing does have units. Entropy does have units. We're not going to worry about them. We're interested in relative changes to start with. So if we consider glucose and oxygen, so we're considering here, the entropy is low. The atoms are locked together in a certain configuration, and so they can't be distributed more randomly because they've got to be bonded together, and so entropy is low. So that's not a random distribution. There are many fewer ways that the atoms can be organized to make glucose. In fact, there's only probably 2 or 3 ways, given that there are isomers of glucose. Now, if we take those atoms in glucose and oxygen and we rearrange them into carbon dioxide and water, now we've got lots and lots of variability in terms of how we can arrange the atoms and how those molecules can be distributed in space. And so there is now a much greater distribution of states of the atoms and the molecules, and so the entropy has gone up. Things have become much more random. So as we go from glucose and oxygen to water and carbon dioxide, the entropy has increased, and we can start to think about this during photosynthesis. Now, fortunately, photosynthesis is actually just chemically the reversal of cellular respiration. So if we take water and carbon dioxide, I say we, I mean plants, if plants take water and carbon dioxide and they rearrange those atoms through the chemical processes of photosynthesis, you get glucose and oxygen. This makes sense. Plants need carbon dioxide and they produce sugars and oxygen. And so we can start now to think about the relationship between the reactants on the left and the products on the right in terms of free energy and entropy. So I've got a whole bunch of questions now, which as we work through them, hopefully you will start to build up an understanding. And if I need to, I'll pause and discuss the question. If I think it's an easy enough question, I'll just flash the answer up on the screen like I've done before. Okay, so let's get started with these questions. Here comes the first one. Entropy decreases as sugars are made by photosynthesis. Let's see how you get on with that one, and I'll flash the answer up in a moment. Okay, here comes our next question. Entropy decreases as glucose molecules are condensed to form glycogen. Let's talk about this one a little bit. Okay, so remember that glycogen is a polymer of glucose. We talked about macromolecules. I talked a little bit about glycogen and said it's just a chain, a branched chain of glucose molecules. So here we are building complexity. We're reducing the number of ways in which a random puddle of glucose can be distributed into a discrete structure. And so what's happened there is entropy has dropped. So yes, this is true. Okay, let's now take a look at a different example with a different question. What about protein synthesis? Protein synthesis results in an increase in entropy. Think back to protein synthesis. I'll stop and let you think about this one. Okay, so the next slide isn't a question. It's actually something that I want you to stop the video and do. So in a moment, stop the video, and then I want you to write a few sentences which explain what changes in entropy and free energy occur as nucleotides are linked together to form molecules of DNA. So go back to thinking about what is DNA, what happens when I link these nucleotides together via condensation chemistry. So stop the video and write something down, throw it into a discussion in Canvas, and we can compare and comment on people's responses to this statement. Okay, so let's just put a couple of things together before we move on and do some more questions. I've got another 5 or so questions to take a look at here, and I'll preface those questions with saying these are the kinds of things that you're going to see on your quizzes. These are the kinds of questions I'm going to ask you. So if you can work through these and actually do them, you're preparing yourself for your quizzes. So back to the graph that we've kind of looked at in terms of free energy and in terms of entropy in the context of cellular respiration. So glucose and oxygen are converted to water and carbon dioxide. Now, you can start to see some relationships between free energy and entropy when we look at an energy transformation like this. So if we look at the free energy in glucose and oxygen, it's relatively high compared to the free energy in carbon dioxide and water. So that was the first graph that I showed you. The second graph I showed you that entropy in glucose and oxygen is relatively low, but in carbon dioxide and water it's relatively high. So we now start to see a relationship between the amount of free energy and the amount of entropy that certain molecules have. So if you've got very high free energy, like in glucose, the entropy is going to be pretty low. But if we convert that glucose to carbon dioxide and water, and we extract chemical potential energy that's contained in the bonds of glucose and oxygen, as what happens is we end up with less energy, and where the energy goes we'll talk about mechanistically through the processes of cellular respiration. But the molecules that are produced are much, much less I don't want to say organized, but I'm going to. As what I'm going to say is they're more randomly distributed. They can exist in many more states in terms of space they can occupy. You can think about water and carbon dioxide diffusing away versus glucose being organized into a little pile of what looks like sand, to be honest. So we can put these things together. Molecules which have low energy tend to have higher entropy. Molecules with high energy tend to have lower entropy. These are relative relationships. There is a mathematical explanation of this in your textbooks. I don't like the mathematical explanations because I think it freaks people out. We're not going to look into that. We're more interested in these relative changes. I'm going to leave the mathematical explanations of this to my colleagues in chemistry. So let's take a look at some more questions, and I'm just going to flick through these. I'll pause and then put the answer up. So here we go. Here's the first question. Okay, here's your second question in this set. Here's the third question. Okay, here's the penultimate one. There's only one left after this one. And then lastly, okay, so I'm actually going to skip back to a question, and so I want to take a look at this question here. This was the second one in the series. The energy released as glucose and oxygen are converted to carbon dioxide and water is converted to the molecule ATP. And so when I ask this question in my face-to-face classes, or when I ask this question generally, people say, yeah, this is true, this is what happens. The energy is converted into ATP. And that's not technically true. The correct answer to this is false. This isn't actually what happens. Is what this says, that the statement says that energy is converted to matter, and except in the center of some suns where certain nuclear reactions are occurring, you can't convert energy into matter, not at least at the level of introductory biology and college chemistry anyway. So you can't convert the energy into matter as far as we're concerned. The second question is a little bit kind of more, this one's better phrased. The energy released as glucose and oxygen are converted into carbon dioxide and water can be used to make the molecule ATP. This is what's happening in cellular respiration. We break down glucose and oxygen, and the energy that's released, some of that free energy can be put into the processes which synthesize, they make the molecule ATP. And so the energy is being transformed from one chemical energy form in terms of glucose to another chemical energy form in the form of ATP. But we're not taking energy and making matter. We can't do that. So we will wrap up there, and when we come back we will carry on thinking about the relationship between free energy and entropy, and we'll start talking about some energy, some energetics and some enzymes in terms of biochemical reactions. So I will see you next time.